Let us look at finding inverse of a matrix using elementary operations. Now, previously we were finding the inverse of a matrix using adjoint of A and the determinant of A. And using the formula, we would arrive at, say, matrix B, which would be the inverse of the matrix A. Now, let's see how to find it using elementary operations. The concept is simple. If a sequence of elementary row operations on a non-singular matrix A transforms it into an identity matrix, then the same sequence of row operations to I, the identity, produces A inverse. So let's look at this with an example. Let's say we have this matrix A. So A is equal to I times A. Pre-multiplying A by I does not change A. It remains A. So in matrix form, we write like this. Now we apply the same row operations on both sides. These operations correspond to left multiplication by elementary matrices. Now remember, we need to carry out this row operation only on the identity. We don't have to do it on A on this side as well. Why? Because remember the theorem, applying an operation to a product is the same as applying it to the prefactor and then multiplying by A. So we need to apply it only to the identity. And you know what is the objective of applying this row operation? Because then only we can decide which particular row operations we need to apply. So the objective is to make the left-hand side matrix equal to identity. Once we are able to achieve identity on the left-hand side, then this matrix would be the required inverse. We start applying the row operations. R2 minus R1. Row 2 minus row 1. 1 minus 1, 0. 3 minus 1, 2. Minus 3 minus 3, minus 6. Now the same row operation we also apply to the identity on this side. So 0 minus 1, minus 1. 1 minus 0, 0. 1. 0 minus 0, 0. Then R3 plus 2, R1. Then R2 by 2, R3 by 2. You can pause the video and look at it step by step. Keep carrying out. Now notice that we are trying to get all the entries below 1 as 0. So here this has become 0, 0, this has become 0, this has become 0. We keep carrying out the operations, required operations, so that on the left-hand side, we end up with identity. And the same operations we are applying on the right-hand side identity matrix it's also. So the left-hand side matrix transforms to identity and the right-hand side pre-multiplier matrix becomes a matrix with some entries. Now, remember, a matrix multiplied by another matrix, if it gives identity, it means they are inverses of each other. So since this matrix when multiplied on the left of A gives the identity, it must be A inverse. So A inverse is equal to this. Similarly, using elementary column operations, we can obtain a matrix which when multiplied on the right of A gives the identity. In either case, we obtain the inverse of A. That was finding the inverse using elementary operations.